Now we are going to introduce a new concept called an ideal, which corresponds to, the way of analogy is that normal subgroups are to groups what ideals are to rings. At least that's one way to think of things, as you will see. That every theorem we have about normal subgroups and groups, you're going to find a corresponding theorem for ideals and rings, even if the actual definition is going to turn out to be very different. So now I want to motivate a new idea for rings, but I want to motivate it by going back and looking at normal subgroups. And so here's our motivating question. What is special about the kernel of a ring homomorphism? So recall for groups, we had proved the following theorem. Given a subgroup N of G, N is a kernel of some group homomorphism if and only if N was a normal subgroup in G. So the proof was that if N was a normal subgroup in G, there was a natural surjection onto then the quotient group was a group as well, and this natural surjection was a homomorphism. And so that would, with kernel given by N. And likewise, we proved that if N was the kernel of a homomorphism, then it was normal. So one would like to prove a similar theorem about rings. When is a subring the kernel of a ring homomorphism? And so here's the key idea you notice very quickly. So the kernel of a ring are the elements that are sent to 0. And one identity we know about 0 is that multiplication by 0 gives you 0. And so let's see what happens when you multiply an element in the ring by an element in a kernel. Well, since phi is multiplicative, you get phi of r times phi of s. If phi of s is 0, you get phi of r times 0, which is 0. Similarly, that's phi of s times r as well, by the same logic, just in reverse order. So what you see is that if you take an element in the kernel and multiply it on the left or the right by any other element in the ring, you get another element in the kernel. So the kernel is not only a subring of R, it's got this extra special property. And one of the facts we're eventually going to show is that this property characterizes kernels of ring homomorphisms. So this property has a name. We're going to call it being an ideal. So let I be a subring of R, then I is an ideal of R if for any element in the ring and any element in the ideal, the product R times S is in the element of the ideal. Technically, this is what you call a left ideal. And then you have two-sided ideal if you get both products. In the traditional class, I sometimes go through the history of where the notion of ideal came from. It originated in the study of number theory related to Fermat's last theorem, but it has lots of other applications. You can also motivate it from the study of the solutions to multivariable polynomial equations. The point is that there's at least 3 different areas from where ideals just naturally pop out of. So the perspective we're taking from this course is just straight algebra, this notion of kernel. First thing you note is we have these 2 requirements. So note the main difference between a subring and an ideal is that, remember, a subring is closed under products in I. The main difference here is we're multiplying, but one of the elements is in I and the other one is actually in the larger ring. So this is a more general property. It's not just products of elements in I are also in I. It's product of any element in I by any element in the larger set is still in I. And so you see that there's an easier way to show I as an ideal. Instead of showing that it's a subring first, you just show these 3 conditions. So I is non-empty, it's closed under subtraction, and then this 3rd condition, for any element in R and any element in I, the product is also in I. And the reason why that is sufficient is because in order to be a subring, you had to have this condition, that for any two elements in I, their product is in I. But if R is in I, then R is in, if this element is in the ideal, then it's also in the larger ring. And so this property for being a subring already follows from this condition. So to actually show something is an ideal, you don't need to show it's a subring first. You just need to check these three facts. Most importantly, you do always need to check that it's closed under differences. Unless your ring has a unit. If that happens, then you get away with skipping this step too, I think. Let's think about that. Because if your ring has a unit, the -1 is in the ring, and so then you definitely have additive inverses. Yeah, you'd still have to show closure under addition. So if 1 is in the ring, then you could replace this with closure under addition. Because then this condition here will allow you to conclude that -s is an element of I for every s in I. But you can't quite get all the way to closure under addition directly, so you do actually need to show this part. All right, so we have a new definition of ideals. Let's look at some examples. Let's look at the first one. Our first example is the subset containing only 0. This is actually an ideal. Why? Because if you take any element in R, if you multiply it by 0, you get 0. Which is definitely an element in this set. Similarly, if you take any two elements in this set, well, the only choices are both 0, then their difference is also 0. So clearly this is an ideal. And the set's non-empty, so it satisfies our three conditions. This is known as the trivial ideal. So usually when we say proper ideal, similarly R is also an ideal. Of itself. So normally when we say proper ideal, we're ignoring these two cases and we want something else. So let's look at another example. How about multiples of an integer? So I claim that multiples of an integer, n, is an ideal of the integers. Let's prove it. One thing we already know, and we've shown nz is a subring. So we already have that fact. Because we already know that fact, the only thing we need to check is given an r in z and an s in nz, that rs is in nz. And I actually hinted at that before when we proved that nz was a subring. I pointed out that one of the facts, the way we had done the proof, I noted we had taken two elements in the subring, and we showed that the product was in the subring, and I noted that one of the assumptions we didn't even use. So this is why, because actually we have an ideal. So S is a multiple of n. S is equal to Q times n. R times S is equal to R times Q times n. Associativity holds, and look, R times S is a multiple of n. So this is a generalization of the fact that when you multiply any number by an even number, you get an even number. If you multiply any number by a multiple of 3, you get a multiple of 3. So on and so forth. So this is an ideal. And in some sense, that's what an ideal is. It's a generalization of the concept of multiples. And in fact, our third example of a principal ideal could be viewed as a generalization of the concept of a direct generalization of the concept of multiples, or basically a generalization of cyclic subgroup in some sense. This is a special type. Given an element to the ring, this is going to be the smallest ideal generated by the ring, by that element. It's always going to be denoted parentheses A. and they call this the principal ideal generated by A, and it consists of all multiples of the form Ra times A, where R is an element in R. So when you're working with the integers and n is an integer, this is nz. Worth pointing that out. And for arbitrary rings, the ideal generated by 0 was the trivial ideal. And if your ring has a unit, the ideal generated by 1 usually ends up being the full ring. All right, so I'm going to assume that your ring has a unit in order to prove that this ideal is non-empty. If you don't have a unit, you're not guaranteed that this ideal is even non-empty. Why? Because this guarantees that you actually have A as an element in the principal ideal. All right, so we need to show that we're closed under subtraction and closed under products where S is in this ideal and R is not. So we're going to take R in the ring and S in the ideal. Then S is a multiple of A for some factor in the larger ring. All right, now to prove subtract closure under differences, we need to remind ourselves that actually we need little r to be in the ideal as well. Then little r is also a multiple of A for some factor r double prime. Now what's r minus s? It's r double prime A minus r prime A. You can factor out the common factor of A, and look, we have a multiple of A. So the difference of two elements in the ideal is an element in the ideal. Likewise, for part 2, now we're back to our original assumption. R is just an arbitrary element in the ring. R times S is R times R prime A. By associativity, we get another multiple of A. So this actually is an ideal. As one final example, take the polynomial ring with integer coefficients. Let I be the set of polynomials such that the constant term is congruent to 0 mod 2. In other words, the constant term is even. If you take any two polynomials with even constant term, then their difference also has even constant term. If you take another polynomial and multiply it by p of x, the resulting constant term is also even. So you can check that this is in fact an ideal. And we won't prove it in this course, but you can check that this ideal is actually what they call finitely generated. In other words, every polynomial here can be written as in some sense this is a basis, the polynomial x. So every polynomial is a linear polynomial combination of something times x plus something times 2. Now why would that make sense? Well, because this has an even constant term and this has an even constant term. But the obvious problem here is that there's really no way to get down to one polynomial, because there's no polynomial with even constant term that divides both of these if you're working over the integers. So this is here to point out that not every ideal is a principal ideal. This is actually kind of important because this is actually the origin of the study of ideals. They originally introduced because there were cases in number theory where where they were studying factorization in certain types of rings, and they were assuming unique factorization held, and it didn't, and it's because it actually held for these types of ideals that aren't principal.